Hi, welcome to Chapter 3, Arithmetic for Computers in our Computer Organization class. And in this chapter, we will discuss the computer arithmetic operations uh, like the addition, subtraction, multiplication, division, floating point, and primitive design for ALU. Um, Obviously, the operations in computers can be either of integer format or floating point format, and the integers basically are faster, but you have some kind of issues of representing the fractions. There are the fixed point and all these solutions, but ultimately the precision uh, and the long range is provided by the floating point format. Okay, and that's why people use them when dealing with tiny little numbers, when they want accuracy and when you have very large numbers. So floating point are preferred. Uh, One thing about floating points that they take extensive amount of processing compared to integers, so they tend to have higher delay and higher power dissipation and energy dissipation. So use them when you need them. That's the point. So we'll study the floating point at the end of the chapter. Now, in terms of additions, we have studied this earlier in our class in digital logic, and let's do some kind of refreshment in the whiteboard. In terms of when you are adding numbers, um, the numbers can be either represented as signed or unsigned. Okay, so so the signed number, let's just take for example 1100. If I treat this number as unsigned, I'm sorry, as signed, so obviously this 1100 is a negative number because of the fact the most significant bit is a 1. So to know what is this number, it's minus what. So what do? I take this number, I take the 2's complement, and obviously the 2's complement is 4, so therefore this number must be minus 4. Now if I treat this number as unsigned, so this is simply 12 in the decimal format. Okay, so obviously what is the type of the number must be known at the that you are able to interpret the representation of the number correctly. Now, let's go back and review some of the additions. So this is important for us to understand. So now suppose I am doing signed math. Okay, the unsigned math is really not that hard to do. So the real challenge for the unsigned math. And so let's so signed math. Now suppose I'm adding two numbers here. Let's say 0, 1, 1, 0 plus 0, 0, 1, 0. And so clearly I'm adding here, let's just say for now, this is 0, 1. Okay, so I add, obviously, as we have learned in previous class, I will add digit by digit. So 0 plus 1, that's a 1. 1 plus 0, that's a 1. 1 plus 0, that's a 1. And 0 plus 0, that is a 0. So obviously what I'm doing here, I'm adding plus 6 plus 1, right? Oops, sorry, plus 1. And that results in plus 7. Okay? Now, let's try to do now the case of um, let's try to do now the case of subtraction. 0 1 1 0 minus 0 0 0 1. In this case, the subtraction, I have to represent this number in its 2's complement. So what do I do? I say, okay, so let's add 0 1 1 0 with the 2's complement of this number, which is 1 1 1 1. Okay, so let's add now. So 0 plus 1, that's a 1. 1 plus 1, that is a sum of a 0 and a carry of a 1. 1 plus 1 plus 1, a carry is a sum of a 1 and a carry of a 1. 1 plus 0 plus 1, it is a 0 and a carry of a 1. Now, here is an interesting point that we need to observe. First of all, this turned out to be number 5, which makes sense because what I'm doing here really, I'm subtracting 6 minus plus 1. So you would to expect to get a plus 5. More importantly, in these two examples, if you look at this example here earlier, okay, the um, the carry in to the last bit is 0 and the carry out is 0. So both agree. And in this case, I would say that my result is correct and I have no overflow. Okay. Now let's take a look here at the last bit here. The carry in to the last bit, the most significant bit is 1 and the carry out is 1. They both agree. So my result is correct and no overflow. Okay. All right. Good. So what happened when I have an overflow? Okay, well, let's take a look when we have an overflow. So here's an example of an overflow. Okay, so let's take an example of an overflow where I have, let's say, for example, 0 1 1 0 plus 0 1 0 0. Okay, let's add these two. Okay, now 0 plus 0 is 0. 1 plus 0, it is a 1. And 1 plus 1, it is a 0 with a carry in of, to the last bit of 1. 1 plus 0 plus 0 is a 1 and a carry out of a 0. Now let's check here. This is the most significant bit position. The carry into it is 1. The carry out is 0. They do not agree. They do not agree. So now this means my result is not correct. Why? Because I have overflow. Okay, so let's check that. What am I doing here? What am I doing is I'm adding plus 6 plus 4. Okay, I should get a 10, but I'm not getting a 10. I'm getting a negative number here. Okay, um, so interestingly enough, this is so let's take the 2's complement here. So the 2's complement is 0 1 1 0. So this number here is minus 6. So it doesn't make sense that I'm adding plus 4 plus 6 plus 4 and I get minus 6. Well, this is why we are saying you have incorrect result because of an overflow. What is an overflow? Well, the overflow is simply we have our number system collapsed. You see, in 4-bit digit, right, we can represent numbers from 0, 1, all the way to +7. And in the negative side, -1 all the way to -8. Because in 2's complement, I can represent things from -2 to the n -1 all the way to +2 to the n -1 -1. In my example, n equals 4 bits. Okay, now what happened when I'm adding numbers? So this is the range of number that I have in my available system. Okay, and this system, that's how much. Overflow means the results is outside this range, and therefore the number system, given the number of bits, cannot represent the numbers. We call this an overflow. Okay, there is another thing people use, which is underflow. And underflow is used for floating points, and this is when we have tiny little fractions, all right, which cannot be represented in the system, so we call those underflow, but they don't show up in an integer operations. Okay, so overflow means my result is incorrect, typically detected by the mismatch in the carry in and carry out of the last bit in my math. Okay, addition or subtraction. All right, so this is basically what I wanted to say in these few slides. Okay, and these are extra examples for you to look at. And he's showing here that we have signed and unsigned math. For unsigned math, just for your information, typically there is no overflow. Okay, we ignore overflow. This is from programming perspective, but in assigned math, if we get an overflow, okay, this will cause an exception. And an exception, we will study this in chapter 5 and how we handle the exception. But just to give you a quick view, an exception is something wrong went inside the CPU. All right, let's just say, for example, if I am conducting a class session and one student is just turning on his music in the phone, and that is causing disturbance in the class, so now I will stop everything and say, okay, who's doing that? Let's just stop doing everything because we cannot conduct the class. So we have to handle this issue that happened internal to our class. This is the kind of exceptions. So an example, the CPU takes action, and typically the overflow is a very serious condition because you cannot really represent the results. Another condition in math that happen often, if programmers are not careful, is divide by zero. Okay, right. Okay, now multiplication. So we are done with a quick review of the addition and subtraction, and let's discuss now multiplication. And we will do multiplication of two unsigned numbers. And multiplication of two unsigned numbers, typically we multiply two numbers. The top number, we call it the multiplicand. The bottom number, we call it the multiplier. And basically the multiplication is done exactly the way we multiply decimal numbers. So we start with the least significant digit, which is in binary, it's either a 1 or a 0. Then we multiply it with the multiplicand. So basically the multiplicand, we either copy it or not copy it, because this digit is either a 1 or a 0. So if it is a 1, we copy the multiplicand. If it is a 0, this bit, we copy zeros. instead of the multiplicand. So this digit happens to be a 1, so we put the multiplicand here. Then we move to the next digit of the multiplier, and we multiply this digit with the multiplicand. This happened to be a 0, so we place 4 zeros here. Then we move to the next digit, which happened to be a 0, this third digit of the multiplier, and therefore we put here zeros. And then we move to the fourth digit of the multiplier, which is in this case a 1, and we copy a 1 for we copy the multiplicand. Notice here the shifting that happens in every step, right? And this shifting is because of the weight of these digits. If you look here, this multiplier, the very first bit has a weight of 2 to the 0. The second bit has a weight 2 to the 1, 2 to the 2, and 2 to the 3. And that's why we shift these results. Okay, we call those results partial product. Partial product. Okay, and because at the end we need to add them, so this 0 comes down here, this 0 plus 0 0, 0 plus 0 plus 0 0, and then 1 plus 0 plus 1 da 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 da. Okay, so and this then we finally compute the final product right here. Okay, now so the question is, how can I do multiplication in hardware? And the answer is very simple. What we need is a register of 64-bit for the multiplicand. And the reason we need this register, okay, let me just stop here if I can. Okay, so in this hardware, what we need is a multiplicand. Remember, the multiplicand is the number is at the top. This is the multiplicand. Multiplicand. And this is the multiplier. Okay, right. So what I need here is a multiplicand, which is a 64-bit. We assume our data size is 32. In this example, to make things short, we are assuming that the data size is 4-bit. But since we are designing for MIPS, okay, so we put the real sizes here. So we need a 64-bit for the multiplicand. We need the product, okay, 64-bit, and we continuously add the multiplicand with the product, so we need a 64-bit ALU. For the multiplier here, we need a 32-bit with the capability of shifting to the right, and the multiplicand with the capability with shifting to the left. So initially, when we start the algorithm, we start with the basically the we start basically with the product which has 0 inside it. There is nothing here. Then we initialize this multiplier with the bits, which is 1 0 0 1. Okay, and the multiplicand comes here and saved as 1 0 0 0. Then what we do is we first shift to the right, shift this bit, which is this one here, shift it to the right, and it goes to this control section. This control sees if it is a 1, then what we do, we add the multiplicand, which is in this case 1 0 0 0, to what's in the product register, which is a 0. So as a result, I have 1 0 0 0. Okay, which is basically this stage right here. Now I shift the multiplier one more position, so I get this bit, which is a 0. This 0 comes down to this control circuit. This control circuit sees this, and it adds, instead of multiplicand, it adds zeros, right, to the product. Now the product is what? 1 0 0 0. Now in this by the way, the multiplicand has been shifted by 1 bit position, but it didn't matter because we are adding 0. Okay, Now, why we are adding one bit position here? Because remember, every time I move into the next step, the multiplicand must be shifted to the left. So see, the last step, for example, I'm adding this 1 0 0 0 0. So these have been shifted, right? Shifted to the left, okay, by the steps that as I do the multiplier. So I'll then I shift this 0, then I shift this 1, okay, and then when I shift this 1, I will add the 1 0 0, what's inside the product, with the 1 0 0 0 0. Let's see, that's 4 1 0 0 0, and I have 3 zeros here as well, okay, and then I will get 1 0 0 1 0 0 0, okay, which is the final result after shifting all the bits for the multiplier. So finally the multiplier, what's inside here is just zeros, and what's in here is the maximum shift, which is right here, and what's inside the product is the final result, okay, which is 1 0 0 1 0 0 0. Okay, in the exam I want you to show typically I will ask you to draw this hardware, if for example, and I ask about the final results on these registers and their initial values. So you make sure you understand the algorithm very well as I explained it. All right, make sure you know that how we initialize these registers, and make sure what's their final value. Okay, and also typically in the exam we express the numbers in these registers in hexadecimal. Okay, because we typically deal with 32 bit sizes. Okay, now what happened is that there is a more optimized multiplier. Okay, and what do you mean by optimized? Well, it is optimized in terms of size. It is less smaller in size. Smaller. Why smaller? Well, notice here he's presenting in the solution a 32-bit ALU, and in the previous solution that we have, which is not optimized solution, it was 64. Significant gain and reduction in area. Also notice that here he is using multiplicand, okay? He's using here multiplicand of, let's see, multiplicand of 32-bit. In the previous solution, we have a 64-bit register multiplicand, so significant saving as well in this solution. Notice here is that we do not have multiplier, where when the previous solution we had 32-bit register multiplier, also significant win. And the product we have 64-bit as before, so 64-bit, the product register did not change. Okay, so this is optimized, which has size is much smaller, okay, than the previous solution. But obviously there is a cost for that. And what's the cost? This is a little bit more difficult algorithm. So let's see how we do this. To start, what we do in this algorithm, in this product register, we initialize it by placing, okay, by placing the multiplier in this product register. So this product register is a register with shift to the right. It's capable of shifting to the right, but initialized here with the multiplier. So here we in the least significant half of it, we place the multiplier. And what about the upper? Why? Because notice the multiplier is 32-bit. Okay, for in MIPS architecture. How about here? What do we initialize here? Zeros, zeros. Okay, then what we do? Then what we do is that we shift to the right the multiplier to test the very first bit. And based on this bit being a 0 or a 1, all right, then we tell this control circuit whether to add the multiplicand, which is a 32-bit in this 32 ALU, to the uppermost 32-bit here. So this is the uppermost 32-bit of the product. Okay, so if it is a 1, we add, right? If this a 1, we add. If this is a 0, right, we do not add, no add. Okay, right? So, and then we write the result. Notice when we write the result, we shift the register to the right, and thereby we are testing the next bit of the multiplier, and at the same time we are shifting the product to the right. We are increasing the significance of the bits by 2, by multiplying it by 2. Okay, and then we continue shifting the multiplier to the right and testing bits, and then shifting the result of the product bit by bit. And at the end of the algorithm, what you will see here in the 64-bit is the final product, right? And in here, the multiplicand register does not change, stays as the same. Okay, and with this dual use of this register, notice this register initialized with the multiplier, and then finally it will be populated with a 64-bit of the results. Obviously, a little bit more complex algorithm, but with significant saving in the area. Okay. Now, in MIPS multiplication, we have two registers that is used for the multiplication, which is the high and low register. So typically, when we multiply let's say if we use this instruction mult these two registers, right, or mult unsigned, the result will be in these high and low registers. So let's say we say mult T0 and T1, okay? The result of this multiplication, so because every one of those 32-bit, the result has to go into a 64-bit, and this is the 64-bit, the high and the low registers. These are specifically dedicated for multiplication and division operations. Then, how can I access these two registers? Well, then you use these instructions, move high and move low, and basically if you want this result to go to S0, you go move high, okay, to S0. So and then so you take this result and put it in S0. Then you say move low, okay, to S1, and you move this result to S1. You cannot access the high and low without these two instructions, okay? All right. Now, suppose I want to do much like the add operation. I want, because see here I have two operands, the sources, and the destination goes to these high and low. Suppose I want the destination to be in my instruction, much like I do an add operation, like what I do here, which is the destination register gets the multiplication of RS and RT. Well, the MIPS architecture allows you, provided the result finally fits in 32-bit, and this is fine and okay if you know that your numbers are very small and the result fits in. So suppose, for example, you can say mul let's say S1 gets the S2 multiplied by S3, and I know that the numbers here that I'm dealing with, they range from, let's say, 1 to 8, here 1 to 8, and in this case I know if I multiply them I will not exceed the 32-bit size of S1. Then this is fine that to use the mul instruction. Okay, so okay, with that we have explained the multiplication operation in MIPS architecture, and we will discuss division in next lecture. Thank you very much.